Ladies and gentlemen, welcome to the Big Bear Math Channel. We're cruising through the 2019 AP Calculus BC packet where we're making a stop here on question number 4. Great question for both AB and BC students here. I think you're going to see three major themes. Number one, you're going to see a really nice related rates question. Number two, we're going to see a challenging implicit derivative when we get to part B. And then we're going to finish it off in part C by solving a differential equation using a separation of variables. So let's take a good peek here at the opening paragraph. It says we've got a cylindrical barrel with a diameter of 2 feet. Now I want to pause right there and mention this diameter is going to be a constant. So no matter whether the water is really full, half full, or getting empty, the diameter is always going to be 2, and therefore the radius is always going to be 1. We love constants. Constants are our best friends, especially as we get ready to do a related rate. We've got water's draining out the bottom. The rate at which the height is changing is modeled by this function right here. And now part A wants us to find the rate of change of the volume of the water in that barrel. And you'll notice they did give us this really nice volume formula. Now, at first glance, you're going to look at volume and you're going to say, well, it's in terms of two variables. Of course, pi is the constant, but you've got r and you've got h. And so you're thinking, oh my gosh, okay, I can derive this with respect to time using the product rule. But like we said back here when we were talking about the diameter being a constant and the radius being a constant, we shouldn't have to do any crazy product rule. In fact, I think this is going to go down in history as one of the easier related rates questions you're going to end up seeing. So before I derive, I am going to substitute a 1 for that r. This is the one and only time where you're ever allowed to substitute a number in for one of those, original variables before you derived. So volume really is just pi h. And now I'm going to derive this expression with respect to t. So the left side becomes dv dt, and the right side becomes pi multiplied by dh dt. And just a tiny bit of overkill here. The way I'm deriving this is I'm thinking h raised to the first. So I'm doing a little bit of power rule, or chain rule, I should say. So I'm multiplying the 1 times the pi to make pi. This would now be h to the 0 times the derivative of the inside, and that's where the dh dt comes from. Okay, so now what we want to do is we want to figure out, well, what is dv dt when the height is 4? Now you notice there's no h in this equation, so there's no place to directly plug the 4 in. So the question becomes, what is the value of dh dt when h equals 4? Question mark. So use that differential equation that says dh dt is equal to negative 1/10 times the square root of h, which makes negative 1/5. So we're going to say, let's see if I can make a little more room here. dv dt evaluated when h equals 4 becomes pi multiplied by negative 1/5. We could say negative pi over 5. Now the question is, what are your units? What are your units? Let's think about this. What do we know so far? We know that h is measured in feet. Okay, so and that means volume is going to be measured in cubic feet. All right, so in essence, always take a peek right here. This is going to help you with your units. What is your volume measured in? What is your time measured in? So it's going to be cubic feet per second. All right. So we always work so hard to have good notation, and here's where it can kind of work for you is by asking yourself what the units here and here are. It tells you what your units are going to be on your answer. All right, we're going to have fun with part B. This has probably got the biggest bear trap of this entire problem right here in part B. So they said at the moment when the height is 3 feet, is the rate of change of h, okay, let's highlight that right there, is the rate of change of h, that's your dh dt, is that value increasing or decreasing at the particular moment when h equals 3? So in other words, what we're really asking ourselves, is dh dt increasing or decreasing at the moment when h equals 3, okay? Now, what we want to investigate is the derivative of dH dt. Okay, so basically, is the second derivative of h going to be positive or negative at h equals 3? That's what we need to know. So for instance, if we found out that the second derivative of h was positive, we could work backwards and say, well, then dH dt itself has to be increasing. Because remember, you may think of this as the second derivative of h, but what you really want to think of this is this is the first derivative of dH dt. So now here comes the implicit derivative. Let me just make a really subtle move here. I'm not deriving yet. I'm just rewriting the dH dt function as h with parentheses raised to the 1/2. Now you're thinking, why are you using parentheses? I really don't see the necessary need for parentheses. I think it's a little trigger that's going to help you recognize the need for an implicit derivative, because we've got to preach chain rule here. So as I derive, the second derivative of h is going to be, I got to multiply the 1/2 by the negative 1/10 to make negative 1/20. Keep the inner function according to the chain rule. Subtract 1 from the exponent. Now here's the kicker. We need to multiply by the derivative of what was inside these parentheses, right? And the derivative of h with respect to t is written as dH dt. Now what I'm going to do is I am going to take this expression right here and sub it in for this dH dt just to clean it up a whisker. So what's that going to look like now? So the second derivative of h is going to be, let's say, negative 1/20 radical h times, now make your substitution, so it's negative 1/10 radical h. Now this is really wild. You're going to see these radical h's cancel. Multiply the coefficients to get 1/200. And now you get the second derivative isn't even in terms of h. It's just always 1/200. And so there really wasn't even a place to plug that 3 in. We're just going to say the second derivative is always positive. Therefore, dH dt is basically always increasing. But at this particular, we only care about it at h equals 3. So dH dt is increasing at h equals 3 since the second derivative, kill that, dt is greater than 0. All right, very good. Let's go get parsed. All right, the first thing I noticed when I read C is they said when t equals 0, the height of the water is 5 feet. Think of that as your initial condition. So I'm going to make a note to myself here that h of 0 equals 5. Think of that as your initial condition. And you're thinking, what is an initial condition? Well, that's the value. See, after I separate the variables and integrate, I'm going to end up with what's called a general solution, because there's going to be a plus C term at the end. I'm going to use that initial condition to substitute a 0 for t and a 5 for h and solve for c, so that I can basically transform my general solution into a particular solution. But anyway, I'm getting ahead of myself. So let's focus on this technique of separation by of variables. I'm going to multiply this dt to the other side, and then I'm going to divide this radical h to the left side. So really what I have is h to the negative 1/2 dh on the left. I've got negative 1/10 dt on the right. Now, interestingly, we could make a comment here about this coefficient. You could multiply both sides by negative 10 and kind of move that to the left. But what I want to do, I always want to kind of minimize how much traffic I have on the left side here. Because ultimately, after I integrate and then find C, I'm going to try to solve for H on the left side. So the more I can keep on the right side, the more it's going to make my life easier down the road. Okay, now let's go ahead and integrate both sides. This is going to become H to the 1/2 with a coefficient of 2. I could put a plus C there, but it's not necessary. Equals negative 1/10 times T plus C. Okay. If you have any hesitancy right there, you can just derive both sides of the equation that I just wrote and see if the derivative takes you back to the previous line. Now, some people want to solve for H right here. That's totally legit. I usually like to use my initial condition and just find C as early as I can. typically that's my strategy. So I'm going to go 2, 5 to the 1/2 equals negative 1/10 multiplied by 0 plus c. So c itself is going to be 2 radical 5. And I'm just going to slide that bear back in there for c. All right, let's pop up a new color here, shall we? All right. So what I've really got cooking here, kind of split the page in half. I've got 2 radical h equals negative 1/10 t plus 2 radical 5. This is a particular solution, and now all I want to do to finish it off and get my last point and try to lock down a 9 out of 9 is to try to solve for that h. So I'm going to divide everybody by 2. Negative 1/20th t plus radical 5. I'm going to go ahead and square both sides. And you could put those terms in any order. I guess I'm going to try this, radical 5 minus 1/20th t, all squared. And that's it. I'm all done. So a couple of things just to check this answer out. So this answer, you always want to make sure that your final answer here satisfies the initial condition. So if you substitute a 0 right here, you're going to get 5 when you're all done. So we check that. And also, if I derived this expression, it would match the original derivative up here. So other than that, that's all I've got here for this problem. And so I hope you feel a little bit better about getting ready to take that exam. If you found something that was helpful or you like this video, please hit subscribe below, share some comments, share it with your friends. Other than that, keep tackling big bears.